Dear participants, it is my great honor to now present the IAF World Space Award Highlight Lecture on the outstanding Chang'e 4 mission to the Moon. To celebrate this impressive achievement, our colleagues in China have organized a special IAC 2020 watching session, and we should now be able to connect live with them. Hello, Beijing. Thank you very much for joining us live. All this enthusiasm, you are very proud. And now, please give a warm welcome to Mr. Yu Dengyuan, Deputy Director of the Science and Technology Committee at the China Aerospace Science and Technology Corporation.
Distinguished Chairman, ladies and gentlemen, good afternoon. My name is Yu Dengyuan. I'm from China Aerospace Science and Technology Corporation. On behalf of Professor Wu Ren, the Chief Designer of China Lunar Exploration Plan, thank you very much to give us this opportunity to share the Chang'e 4 mission achievements. Today, my topic is technological breakthroughs and scientific progress of the Chang'e 4 mission. This talk includes 4 parts. Part 1 is to introduce what is the China Lunar Exploration Plan before 2020. China Lunar Exploration Plan before 2020 include 3 steps. First is orbiting, second is landing, third is sample return. So far, China has finished 5 missions successfully, which realized respectively orbiting around the Moon and landing near side and far side of the Moon. Part 2 is about development history of the Chang'e 4 mission. Chang'e 4 mission is composed of the top-level mission design segment and 5 affiliated engineering systems, namely the probe system, launch vehicle, launch site, TT&C, and the ground application system. The probe system includes relay communication satellite and the probe. The Chang'e 4 mission has 13 scientific instruments, including 4 international payloads from Germany, Sweden, the Netherlands, and Saudi Arabia. As part of the project, 1 piggyback microsatellite, which is the first of its kind, was developed and then orbited the Moon for astronomical observation. The Chang'e 4 mission includes 2 launches, respectively for the relay communication satellite and the probe by long-march launch vehicle Chang'e 4C and Chang'e 3B. The relay communication satellite Aequire was launched into an Earth-Moon transfer trajectory by Chang'e 4C on 21 May 2018. By conducting several orbital maneuvers and captures, the satellite successfully entered the Lagrange 2-point mission orbit, which was about 70,000 kilometers away from the Moon and 450,000 kilometers away from the Earth. after 24 days and achieved stable operation. The probe was launched on 8 December 2018 by Chang'e 3B into an Earth-Moon transfer trajectory, the apogee of which was 420,000 km. After mid-course corrections, near Moon braking, Moon orbiting, and orbit descending, the probe started powered descent when it was 15 km from the Moon surface. After a 687-second process, including main deceleration, quick adjusting, approaching, hovering, obstacle dodging, and slow descending, the probe safely landed on the pre-selected landing zone, which was inside the Willkommens crater on the far side of the Moon. On 3rd January 2019, the probe completed the separation of the land and the rover, and the two take pictures of each other. Thus, with the support of the relay communication satellite, the probe started the long-term scientific exploration and experimentation. Part 3 is about major technology breakthroughs of the Chang'e 4 mission. The Chang'e 4 mission is a highly innovative and complex project with great technical difficulty and a big international influence. Since its implementation, it has achieved a number of technological breakthroughs, which are many as the following 6 aspects. Number 1. Realized continuous and reliable relay communication between the far side of the Moon and the Earth for the first time in the world. A deep space relay communication scheme based on the regeneration and the retransmission of the signal at the Earth-Moon Lagrange 2-point orbit was proposed. Key technologies such as rapid scanning and the acquisition of remote weak signals and singular demodulation with a performance near enough to the theoretical limits have been broken through. A hollow mission orbit surrounding the Earth-Moon Lagrange 2-point and a third-pass orbit capture method were designed. The Earth-Moon hollow orbit configuration is shown in PPT. Key technologies such as the orbit design and control under the condition of multi-constraints coupling were broken through. The difficulty of stable relay communication between the relay communication satellite and the probe on the far side of the Moon was solved. Number 2. Realized autonomous barrier avoidance and high precision landing on the complex terrain of the far side of the Moon for the first time in the world. Since the terrain of the far side of the moon is rugged, the landing area available for Chang'e 4 is only 5% in size of that of Chang'e 3. Thus, the joint orbit control method based on near-moon braking and circumlunar correction double-layer iteration was invented, which enable landing in the same narrow area at a fixed time and a fixed point on the multi-launch windows. In order to work out the problem of safe landing with up to 7 kilometers of tracking fluctuation, a control method for power descent, which is near vertical landing, was proposed to rely the autonomous selection of landing site and accurate obstacle avoidance ability. The range of obstacle avoidance was as high as 300 meters. Number 3. Relate the indigenous development of radioisotope thermoelectric generator for the first time in China. The production of the highly toxic U-238 space RTG, as well as 19 technologies in 4 categories on comprehensive experimentation and evaluation of safety for space applications, were broken through. Key technology such as RTG design, thermoelectric materials development, and high efficiency heat transfer technology were conquered. The RTG was developed to generate electricity stably under the temperature difference of 210 centigrade. Number 4. Broken through multi-window reliable launch and combined navigation filter optimization technologies for the first time, aiming at the high precision orbit into requirements of the relay communication satellite. A multi-window optimization launch trajectory design method was proposed, which broke through the high precision guidance technology in the multi-interference integrated environment and improved the trajectory entry accuracy of the launch vehicle Chang'e 4C by an order of magnitude. The combined navigation filter optimization technology has been broken through, and the accuracy of launch vehicle Chang'e 3B in orbit has been improved from 1,000 km to 100 km when the apogee heat reaches 420,000 km. Number 5. Related 6-target TT&C for lunar exploration and high precision long-term control of the relay communication satellite in the hollow orbit. The multi-target deep space TT&C scheme realized for the first time reliable TT&C of up to 6 deep space targets, including, among others, the relay communication satellite, the lander, and the microsatellite satellite during the mission period. Number 6. The technology for the world's first circumlunar microsatellite system was broken through. The microsatellite Lunar was launched together with the relay communication satellite. It was the world's first microsatellite which independently completed Earth-to-Moon transfer, braking near the Moon, and orbiting the Moon successfully. It verified the deep space microsatellite platform technology and promoted the development and application of micro-nano satellites in the field of deep space exploration. In addition, the microsatellite was also equipped with an optical camera developed by Saudi Arabia to carry out imaging observation of the Moon. Part 4 is about main-faced scientific results of the Chang'e 4 mission. Chang'e 4 mission was equipped with 13 scientific instruments, among others, 8 scientific payloads and a payload for popularization of science are equipped on the lander and the rover. So far, the lander and the rover have been working steadily on the Moon for more than 22 lunar days, setting a record for the longest movement on the Moon and providing valuable first-hand data for science research. It's the first time to implement the topography, minor composition, and environment exploration of the Moon's far side, and many original scientific results have been obtained. Number 1. Reveal subsurface structure within a depth of 40 meters below the Moon's far side, with the lunar penetrating radar on board the U-2. The lunar subsurface structure and nucleus along the rover route has been investigated. The study reveals for the first time a geological stratification structure below a depth of 40 meters along the rover route of the Moon's far side. Number 2. Preliminary reveal lunar deep-seated materials composition. The data acquired by the visible and near-infrared spectrometer on board U-2 exhibits that the spectral absorption characteristics of lunar nucleus at the Chang'e 4 landing site are obviously different from those of the lunar mare basalts on the lunar near side. The nucleus and the locus within the UTO2 roofing area have similar spectral characteristics, indicating that the both of them may be of the same origin and their spectral characteristics are similar to facing ejector. It further confirmed that the rigorous composition of the landing area of the Chang'e 4 originated mainly from facing ejector and represented the deep-seated material of the South Pole Aequire Basin. Number 3. Aequire space environment data of the Moon's far side. The land of Chang'e 4 is equipped with a lunar neutrons and dosimeter cooperatively developed by China and Germany to detect lunar surface particle radiation and dose. The lower UTO2, equipped with the Sino-Swiss Advanced Small Analyzer for neutrons to observe the energy neutral atom of the roofing site. The lunar neutrons and the dosimetry had made the first ever measurement of the radiation exposed to both charged and neutral particles on the lunar surface. The ASIN measured the energetic neutral atoms at the exploring area of Chang'e 4 Lunar. Number 4. Aequire space singular date with low frequency radio spectrum for the first time. A very low frequency radio spectrometer was developed and mounted on the Chang'e 4 lander. After it landed on Moon's far side, 3 complete high resolution time varying waveform of very low frequency radio waves are required. It is the first time to observe the ultra wideband, very low frequency radio astronomical singular on the Moon's far side surface. Number 5. Conduct a series of scientific experiments. The angle reflector that meets the requirements of relay satellite laser ranging was successfully developed and conducted laser ranging experiment. In addition, a payload of scientific popularization biological experiments were hereby constructed. The germination process of counting seeds in closed environment on the lunar surface was successfully observed. Since the successful implementation of the Chang'e 4 in 2018, a number of technological breakthroughs and scientific achievements have been already made. In the future, China will develop Lunar Research Station prototype and the International Lunar Research Station in the lunar South Polar region to adopt international cooperation. Lunar exploration is the common pursuit of mankind. Let's work together to explore the moon, to learn the moon, and to learn the universe. That's all. Thank you very much. Welcome to Beijing.